Contemporary biology is witnessing a departure from the strictures of reductionism, while the historical focus on decomposing life into fundamental molecular parts yielded immense progress in genetic mapping. It left a conceptual void regarding the nature of the whole. The persistent challenge remains, explaining how a collection of chemical reactions transcends mere physics to become a purposeful agent. As we observe the transition of a quiescent oocyte into a sentient adult, it becomes clear that life is defined by a journey from matter to mind. This realization necessitates a framework where atoms, tissues, and consciousness are treated as interconnected nodes within a singular cross-scale network. The physical spark, Deacon's autogen. The emergence of a self begins with the physics of reciprocal constraint. Terence Deacon provides a solution to the origin of life through the model of the autogen, where two distinct self-organizing processes lock into a state of constraint closure. Metabolism, which provides the energy and building blocks, is inherently dissipative. Left unchecked, it exhausts its resources and fades into entropy. Conversely, the formation of a structural shell requires energy and specific materials. In an autogenic system, these processes become mutually dependent. The metabolic cycle produces the components of the shell, while the shell provides a boundary that prevents the metabolism from dissipating. This creates a self-repairing unit that introduces normativity into the physical world. For the first time, events in the universe have meaning relative to the system. A breach in the shell is objectively detrimental to the system's persistence. This is the birth of the first, most primitive self. Once the individual self is established at the cellular level, the question shifts to how these units coordinate to form higher-order organisms. Michael Levin's bioelectric research shows that cells form an integrated network via gap junctions, electrical bridges enabling direct ion flow. This connectivity facilitates the expansion of what Levin calls the cognitive light cone, the spatial and temporal boundary of an agent's concerns. In a unicellular state, a cell's concern is limited to immediate local survival. However, as cells synchronize their membrane potentials, they begin to feel the physiological states of their neighbors. This shared bioelectric state encodes large-scale morphological blueprints, allowing a collective of cells to act as a singular agent with the goal of building and maintaining a complex organ. The self thus scales up, shifting from the individual cell to the tissue and eventually the entire organism. To formalize these observations, we turn to the abstract language of category theory. This mathematical framework posits a relational network ontology where the identity of any object is defined entirely by its interactions or morphisms with others. From this perspective, we define a cell by its persistent role within a relational network, with its constituent molecules taking a back seat. Topos theory further refines this by introducing the concept of sheaves. A sheaf allows us to understand how local information, the bioelectric state of a single cell, is mathematically glued together to form global information such as the shape of a limb. This logic explains the robustness of life. Even if individual cells are replaced or damaged, the overarching relational network remains stable, ensuring that the global form is preserved. By integrating these three pillars, we arrive at the algebra of self. This synthesis treats complexity as the result of a trio: constraint, information, and relation. Life is defined as a system capable of maintaining and replicating its own relational network. We now understand evolution as more than just shifts in gene frequencies. It also encompasses the evolution of relational patterns. This unified architecture allows us to describe biological phenomena from the origin of life to complex cognition without introducing new, disjointed laws for every level of organization. The implications of this framework are transformative. In medicine, we begin to view cancer as a topological defect, rather than a purely genetic one. When a cell's gap junctions close, it is severed from the tissue's relational network. Its cognitive light cone shrinks, and it reverts to the ancient selfish autogen program of proliferation. Restoration of these bioelectric connections can force the cell to remember its role in the collective, effectively reprogramming it back into the body. In engineering, this logic enables the creation of xenobots, living robots built from skin cells that self-organize into new morphologies. This marks a shift toward agential engineering, where we guide the goals of autonomous components rather than dictating every movement. Similarly, in artificial intelligence, we are exploring virtual autogens, code blocks that must maintain their own data metabolism to survive. This creates AIs with skin in the game, ensuring an intrinsic commitment to accuracy and truth. The algebra of self signifies a fundamental shift from a mechanistic to a relational understanding of life. This perspective reminds us the essence of our existence lies in sustaining the relations that define us, with the specific matter of our composition being secondary. By treating biological components as agents within a network, we unlock new paths for solving medical, environmental, and computational challenges. We are stepping into an era where our work extends beyond repairing biological machines. We now innovate and restore the relational networks that underpin the world itself.